Hey guys, this is Carrie, and in this video we're going to be making the answer key for homework 7. It might be a little noisy in here because I'm in 447, but I've got to get this done before tutoring. So here we go. Let f of x equal this. Determine the value of f of 3 minus I. So when we have f of 3 minus I is our input. So we're going to be substituting 3 minus I into the equation everywhere where we see an x. So in order to evaluate this, it looks like we need to do 3 minus I squared, so let's do 3 minus I times 3 minus I. For the next term, we've got negative 4 times 3 minus I, so we'll distribute. We get negative 12 plus 4I, and we have plus 3. So onto the distribution that we outlined for ourselves. We get 3 times 3 is 9. 3 times negative I is negative 3I. Negative I times 3 is negative 3I. Negative I times negative I is positive I squared. We still have the rest of the equation unchanged. So now we get, let's combine like terms here. We get 2 times, and actually we have a hidden like term. If you remember, I squared is actually negative 1. So we can combine this negative 1 with the 9, giving us 8 minus 6i. I'll transcribe the rest down. So we get 16 minus 12i. Minus 12 plus 3, that's negative 9 plus 4i. That gives us 16 minus 9 is 7. Negative 12i plus 4i is negative 8i. All right, on to the next one. So for problem 2, it says, which of the following is the value of I to the 111th power? So in order to figure out what I to the 111th power is, we want to use our diagram where we have 1 on the real axis, I on the imaginary axis, negative 1 on the real axis, negative I on the imaginary axis. And so thinking about powers of I, we know that I to the 0th power would be starting at 1. And so what we need to figure out is how many quarter rotations does 111 correspond to, and thinking about that as full rotations and leftover rotations. So we'll do 111. Because it takes 4 rotations to go all the way around, we'll divide that by 4 to figure out how many full rotations we have. 111 divided by 4 is, stalling for time, 27.75. And so there's a variety of ways that you can do it from here that different people in the class are using. But what this corresponds to is 27 full rotations. Those will put us right back where we started 27 times. And then we have an extra 0.75, an extra 3/4 of a rotation. So that would be 1, 2, 3/4 of a rotation, putting us at negative I. Another way you could think about it would be if you had I to the 112th power, since that's divisible by 4, this is just 1 short of a full rotation, which is also negative I. All right, for problem 3, it says, which of the following is the solution set to the equation, this equation? This looks like a pretty straightforward quadratic formula one, so I'm going to let you guys do this one on your own. I'll do the more complicated quadratic formula one for you. All right, problem 4, this is that more complicated quadratic formula one. So it says, which of the following is the solution set to 2x squared plus 4x minus 1? In order to solve this one, looking at the answer choices, it looks like we need our quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So cringy. I'm in front of like 25 people right now while I'm making this video, but it's okay. X is equal to, let's plug in all of our values. Negative b, well, let's identify a, b, and c. Negative b is going to be negative 4 plus or minus the square root of b squared. Well, that's 4 squared, that's 16, minus 4 times 2 times negative 1. All over twice a, which is 4. X is equal to negative 4 plus or minus the square root of 16. Negative 4 times 2 is negative 8 times negative 1 is plus 8 all over 4. X is equal to negative 4 plus or minus the square root of 24 over 4. And we must be done, except that's none of our answer choices. So there's some way that we can continue from here and get one of our answer choices. And the only thing that we can simplify, it looks like, is square root of 24. So if you break square root of 24 down, you get x is equal to negative 4 plus or minus the square root. And let's just do the factor tree off to the side. 8 times 3, 4 times 2, 2 times 2. So square root of 24 is the square root of 2 times 2 times 3, all over 4. It looks like we can simplify this with the group. So we get x equals negative 4 plus or minus 2 square root of 6 all over 4. And now we can reduce all of these coefficients by the same value. We'll reduce them by 2. So we get negative 2 plus or minus the square root of 6 all over 2, because we can divide each of those by 2. All right, 1 second. Just give me 1 second.
I'm good. I just want to tell you I'm good. I got no kids here. That's it.
Okay, cool. Sorry, Grace. All right, so which of the following equations has a double root? So this is a super throwback to the first day. So we know that when we solve any one of these equations, we're expecting to get 2 solutions. A double root is what happens when those 2 solutions are actually the same answer. 2 solutions that happen to be the same number. And so all of these are solvable using sum and product factoring. But if you think back to completing the square, we know that problem 3 looks like it's going to lead maybe to the same solution twice. So let's see if that intuition serves us well. 2 numbers that sum to negative 6 and have a product of 9. Well, x minus 3 and x minus 3 equals 0. X times x is x squared. That gives you the negative 6 when you sum them. Negative 3 times negative 3 is 9. It looks good. So it looks like our 2 solutions are x equals 3 and x equals 3. So because we got the same solution for both of them, x equals 3 is a double root. So this is the first time that we sort of cheated in order to make the fundamental theorem of algebra true. The fundamental theorem of algebra says that we should get the same number of solutions as the highest power in our polynomial equation. And we do, as long as we consider these 2 separate solutions. So choice 3. All right, this one is a crazy challenge problem. I'm tempted not to give you the answer to it. See what you can do, but we'll solve it. So we get x to the 4th minus 8x squared minus 9 equals 0. And it looks a lot like a sum and product problem, where instead of having x squared, we have x to the 4th. So what I'm going to do is I'm going to try to think, well, what times itself would give us x to the 4th? That'd be x squared times x squared. Now I'm looking for 2 numbers that sum to negative 8 and have a product of negative 9. I think negative 9 times positive 1 will work. So one of these can be factored further by using difference of 2 squares. So we get x minus 3 times x plus 3. The second factor can't be solved any further. X squared plus 1 equals 0. Now before we write down our solutions, since we just talked about the fundamental theorem of algebra, looking at the highest power in our polynomial, it's 4, so we expect 4 solutions. So let's see if we can find them. X minus 3, that has solution 3. X plus 3 gives solution x equals negative 3. And this one, x squared plus 1, doesn't give an obvious solution, but what we can say is the way you find these solutions is each factor can be equal to 0, and that would give us an overall product of 0. So if x squared plus 1 is 0, let's solve this for x. We subtract 1 on both sides. X squared equals negative 1. Last step to solve for x, we take the square root of both sides. Square root cancels the square, and we get x equals, well, because the square root cancels the square, it gives us the positive and negative square root of negative 1. Before this unit, we had no idea what the square root of negative 1 was. In fact, we considered it not a number, but we've seen in this unit that the square root of negative 1 is actually just I, the imaginary number. So we have our 1, 2, 3, 4 solutions to the polynomial problem, and it has satisfied the fundamental theorem of algebra. Amazing. See you guys in class tomorrow.